Let's see how many we have. Okay, I think we better start now. Um, you guys, have you guys ready with the file? Yeah, anyone taking time to?
Yeah, I had a quick read over this morning.
Okay, good. What time did you read?
Sorry?
There was some issue with the file which was uploaded in the file, and around 9, I think I could actually put the right version.
I had a look at it about 20 past 11. I was going over it.
Oh, so cool. By then it was updated one. Okay, just this is the content. Can you guys cross check with your file whether the content, if you press here, table of contents, you get to see. And we are going to cover these topics today. If anyone has a different kind of content set, smaller than this, just go to the course website, reload the file once. All right. If anyone needs time, let me know. I'll wait until you're ready. Seems like everyone is ready. Okay. So today we will be working with MNest, and we'll be working with Keras. This in the last practical we use Keras just to understand how to load data. We will actually spend more time here with deep neural network and how you can actually implement these goals. So we have how do you specify number of layers, number of nodes, and how do you do batch normalization, then regularization, dropout, weight initialization. In fact, we have early stopping condition also. Right. Okay. Just be with me. Keep running. Okay. Well, one cell after the other. What we got here? This we have seen earlier in the first practical. How to, in fact, load data set from Keras. We are working with MNest, so this will import MNest data set from Keras, and we have divided into training set and test set using this command. This you are familiar, and just execute this, and we have a print command where training data shape and testing data shape is printed. You can see that as we are already familiar with 60,000 number of data points for training data and 10,000 for testing data. All right. And could you zoom in a bit? Okay, that's a good thing. Is this better? Or no? That's good. So yeah. And now let's just look into this data. How many classes are there and what are those classes? MNest is a digital number, handwritten numbers, and you know that there are 10 classes and they're actually labeled from 0 to 9. Whereas in Patient MNest, we have 10 classes, but class labels are different. There also we use 0 to 9. But now in MNest, we have, as you can see, there are 10 classes and index from 0 to 9. That means the training date, this train y or test y will have digits consist of uh, 0 to 9. Okay. Once you execute this, what just get an intuition how first image looks, and Okay, maybe I just clear it once. Maybe it's fun to actually clear everything and just run once again from the beginning so that we don't get to see the existing output. You can do it. Just we are at the beginning itself. So let's, okay. This we have done. So cool. There is nothing new. And let's look at how this data actually looks in the array representation. So you notice that this is actually has integer values in each entry, uh, values taken from 0 to 255. So maybe if you're using some other programming R or something, you might actually have a scaled value already. Here it's not the case. So it's important to see whether it's scaled or not. And one more thing to note is that are you guys familiar with one hot encoding? Anyone? No? Okay. So we use this binary classification, right? Here we have 10 classes. It's not binary anymore. So you make use of binary classification, okay, softmax, for example, we want to convert into binary value. So 0 will become a sequence of zeros, okay. Take for 0, we use 10 zeros, 0 to, I think we have this example here. So if label is 5, class is 5, then we put at the fifth position, we put 1 and everywhere else 0. Okay, just this is how we represent. Instead of 5, 5 will be mapped to this vector. So what will happen if the digit label is 3? This is the third position, 0th position, first, second, and third. So there will be 1 here and everywhere else is 0. That representation is called one hot encoded. Okay, anyone? It's just a float value, and we generally like to play with the float values when you are applying tensors, and that's a key reason. Yeah, so just float value, nothing more. So to convert it, first we actually make sure that the data type will be float. We know that the given data is an integer value. So these two lines will make the data type to be float. Once it's converted to float, and we reshape into a vector, okay? Each, yeah, I think 32-bit is sufficient for this problem, because we do not have a large number here, just it's a 255, and should not be a big problem. And similarly, test also is reshaped into vectors, and if you can actually remove this, and because we are, and finally, each entry is normalized by 255, okay, to make it value between 0 and 1. What happens if you execute this cell? See, shape is same thing, but you see that each one became a vector now. So, okay. Did we print here? Yeah, 28 into 28 earlier. Now It's an array of 2-dimension, but now we have 1-dimension array where 70 like 28 and 28 is 784, and that is a vector value. And again we have 60,000 input values and 60,000 output values, and that consists of training set, and another combination is 10,000, just like, but instead each picture is represented as a vector now. And how it looks, if you look at train data, now it's a vector. See, just a vector. The point represents the float value, as someone asked, and every value is between 0 and 1. That's cool. This is just first image in a vectorized form after normalization. Any questions so far? We haven't seen, we haven't converted into one hot. That's what we do now. This is how we do reshaping. We are saying that after reshape, the training data, earlier what is the, say, before reshaping, the shape is 60,000, 28 and 28, isn't it? This is the input for reshape. And what we are saying here that keep number of rows to be, first dimension should be 60,000 only. I don't change that 60,000, but make this a vector. -1 essentially puts one everything in one vector. So instead of 28 by 28, we are specifying that make it is just whatever elements are there, just make it one line, and that's how you get. And after reshaping, what you get is a dimension of 60,784. Is that correct? Yeah. Is this clear?
Yeah, sorry, this is a command that would have really served me during my assignment, so I'm very interested. So for example, if there was another dimension here, if each pixel was then had an RGB colors,
yeah.
So this would retain the 60,000
and
reshape everything below that.
Yeah, that you can just play with a simple matrix, like you take a numpy array, and suppose you are saying how many dimensions you are asking for. This is how much, 3 by 3, suppose. This is a good example. So we got so 3 comma -1. And wait a minute. And what we are saying, maybe this is a bad example. We have 3 input. Wait, what I'm exactly asking?
You've just resized it to the same.
Yeah,
It was
yeah.
already 3 by.
It's like I think I'm taking a.
You'd have to start.
That's true. Like I need to actually have another matrix to
Yeah.
actually. Yeah. Okay. It will delay too much, but essentially, if I actually have say.
Can you just copy and paste that and add it next to?
Yeah, maybe let's do that. And then I think I need to put a bracket. So let's see. So that's good. We have a 2 by 3, and now we are asking b is equal to dot shape -1, say, and you see that, Jed?
Yeah. Okay. So it will. What is,
so
sorry?
let's print what is the value of okay. Sorry. Print a, and that is this matrix, and print b. Yeah.
Okay.
So what it does is that taking first matrix, this is the first matrix, okay, creating a vector out of it, and that is one entry, one row. And because you specified that you want only 2 rows, so first matrix will be vectorized and kept it here, and second matrix will be vectorized. And if you are confused, let's make it 1.1, and for the sake of testing, that's, and you see the output. Yeah, that's what it does. -1 essentially, you can very well say that you can say that, okay, the vector size should be how much is that? 9. You can very well say that 9. I guess that should work in the same way. See, but if you want to give a input independent of this, whether it's 28 by 28 or like 35 by 14 or something, this operation still works, -1. It says that, okay, anything else, just make it vector. That's what it says, -1. You can very well count these numbers and say that, okay, it's 9. In that case, you can very well replace this -1 with 784. If you give any other number other than 784, it will give you an error.
Okay. So can you use reshape to do, like, so you're keeping the complexity down to a certain level and then vectorizing below that? Can you do things other than vectorizing below that? Like, for example, can you
can do it as long as number of elements won't change. You can do any reshaping.
Okay, awesome. Thank you.
Yeah, so you can say that instead of 3 by 3, I don't think 9 can be split in a form. But yeah, you can reshape as long as it's a valid matrix.
Okay, awesome.
Yeah.
Thank you. Is there a website? Sorry, because I'm learning Python for this subject. Is there a website that you can recommend that has good documentation for all of this stuff?
Plenty are there. The way I learn is that if I need something, I Google search. I just practice based on. So it's difficult to actually someone suggesting Stack Overflow. That's where you mostly end up when you're going. But yeah, this documentation is there. Just Google search if you're reshaping a matrix or something, and you get all the possible options available. All right. So, okay, we reshaped and we got this, and we have a. Oh, I screw it up. I guess I did multiple times. Let me. Like normalized twice. So let me do it again. And then we have scaling. This is just example. All right, we're back. So we have values between 0 and 1. And now, does anyone have a question about question about one hot encoding? It's clear, right? How we are changing. If it is 9, then 1 appears here in the 9th position. Okay, and everywhere else is 0. So that's what we are that we are taking training, say, and each entry we are converting to one hot, and this can be done using this package called two categorical. Okay, and just check how actually it looks. So first image class is actually 5, and after one hot encoding, this is one hot encoding 0 gives the first vector, which consists 1 at 5th position. All right. So far it's clear, right? I think Jed, I think you're clear now how to use reshape. It just takes a little bit time, and after that it's clear. Okay. Now we have loaded and we converted the data into one hot outputs of the data into one hot vectors encoding. And now, how do we implement the deep neural network using Keras? Let's look at that. And okay, this is very important. We are going to create a deep neural network with 2 hidden layers. First one has 128 neurons, okay, units, and the second hidden layer is 64. And for output, it's always 10 because we have 10 outputs. Okay. So these are the numbers you can change, but for MNIST data after one hot encoding, we need to keep 10 here. And what are we doing here? The activation function, we are saying that first hidden layer, it's ReLU. And second hidden layer also we are using ReLU. And output, we have discussed in the class that mostly we use softmax. And you can change these things. You just need to Google search how to, what are the options, activation options you have. And that's easy. Just go to Keras website. They have a good documentation and you can quickly find everything. And how to initialize? So there is a class. It's a sequentially we are constructing DNN. So there is a class called sequential that will give you a pointer class name. And once you have this model pointer, we build the network by adding things. So this is add. First tell the system that input layer, okay, that is first layer, 0th layer, has shape. We want shape to be just as future vector. So we already vectorized training data, input data, and training x0 is the first image, that is size is 784 in this case. We are just specifying that if in future, if you want to use some other data instead of MNIST, you don't need to worry. It just always takes what is the input vector size. So the number of nodes in the final layer is the number of classes. Then logic only needs, yeah, that's true. That's correct. What is the activation function you use then for the logistic regression? Krishna?
Sorry, what was that?
For logistic regression, if you use only one,
Yeah.
okay, what is the activation function you're going to use?
The sigmoid.
Yeah, that's it. All right, so here we have two hidden layers. What distinguishes the sequential model? What DNN is a sequential, right? You have input, then hidden layer, then another hidden layer, and then output. That is exactly what you mean by sequential. And okay. All right, guys, executed that this cell. And here just a description of what I just said, and it's ready. And the neural network is ready. We haven't initialized, we haven't compiled where some initial values to begin, and we haven't fitted data. So that's what we do now. And for that, we need to have a back propagation and optimizer. What are the back propagations? Back propagation is clear to you guys, and optimizers we learned already several of these things, and you have seen all of these optimizers. And in this class, we use RMS prop. Okay, you can very well use ADA delta and other optimizers. And again, go to Keras and look for this option optimizer. And what are the optimizers? Optimizer's name is always starts in Keras like this. Keras.optimizers.rms prop or Adam or ADA delta. Okay, and so this is how we compile first. So we are specifying more. Once we have this class, this define the class, and in a class we have how many dense layers we want and what is output activation. Once we do, it has to compile using those inputs, and what is the optimizer we're going to use. All these things will be specified here, and what is the loss function. It's a cross entropy loss function. Okay, and once we specify this, let's look at a summary of this model. You can see first dense layer has that is 0th dense layer. It has uh, uh, output shape like this, because we are saying that it will be inputted to 128, and this is the output shape, and 64 output shape, 10 obviously because output is 10, and you can count right now. This is the specification of this model. Okay. Then it comes to training our model and how we do it. And for this class, we are going to use 25 epochs, 25 iterations in optimization chapter we have. And we are using batches, and each batch has 128, and so 20, and we keep 20% of the data for validation. You guys understood how validation is useful in yesterday's lecture from Benoit. And that means for validation, these are the number of data elements separated, okay, in each step, and these are the number of images we have separated from the training set for validation. Yeah, this is for optimization, and essential validation is used for terminating condition, okay, in the optimizer. This is simple calculation like so with batch size of 128 and we have 48,000 samples in training set. So these many passes it goes to actually make update, and let's look at it how it. So first we need to split training data set into train and validation also. So we use the same train test split to split the training set further into training and validation. And I'm just initializing C21, doesn't matter very much. And once I run this, and you see that 48,000 there is a question. Is that a question? 64 neurons from previous layer plus 10 bias, all going into 10 neurons.
That was a response to the question.
Ah, is it? Okay. There is a question. I missed that. Yeah, I need to make it bigger. Good. So it's clear now. And yeah, this is what we want, the splitting. Input is split into 48,000 and 12,000. And again, output, of course, it has to split. Corresponding output is here and corresponding validation output here. Okay, so we have a training set, validation set, and test set, which already we have separated. If you look at it, for splitting, we are using training one hot outputs, okay? You need to make sure that once you create one hot, you continue to use that. And by mistake, if you give just a train Y, it has only one value and there will be error. So that's, so once we have this, we have a shape of them. And now this is a fitting. We are giving training set, label set that is created from test split, and batch size we are specifying, and how many epochs, verbose is true, and validation data is training valid text, which we got after splitting, and valid labels and validation labels. All good. So everything is good. This fitting essentially, verbose is showing you what is happening. So you will see what is happening. This is now is fitting. You see 375 as we calculated in each epoch. You can see what is happening with accuracy and validation accuracy and validation loss. All right. So done. We are actually trained the, yeah, this is awesome. Actually, we trained the network, and now it's time to actually see the performance. Let's print here. I'm just, you can go through this thing, what are the things I'm printing, and essentially accuracy comes by, this is the fit one I said. So I got a pointer, class pointer, and I can use this pointer to actually find what is the accuracy. Test evaluation is a model evaluator, like just like a way to compute this value more or less across all the platforms are Julia also. It follows similar syntax. So this you get, so on test data, how this model performs. Again, you input and find the accuracy. So you have given test X, and test Y 1 hot. Okay. So we are inputting all this while we use training data and a validation set to fit it. Now it's time to actually see how it performs on test data. So we are evaluating that on test data, and we are saying that variable is 0, so you don't see what is happening, but you can very well put 1, and let's see what happens. And see, that is just applied a test set and showing you on test set what is the accuracy and the loss. And we can print print those things, and we can even plot what happened during training. Okay, how training and validation accuracies changed as you go into 25 epochs. And yeah, I just did jet. If we do 0 here, you just don't see what is happening in the background. Yeah, that line is missing. Okay, so this is for accuracy, this is for loss, seems like, but if you see, you can see that after this point, it's sort of overfitting. Just to clarify, when using the validation set for each epoch, we first train on the training, then use that model on the validation set, and then compute the loss on the validation set.
Sorry, just when we were training, it prints out your validation loss every single time. So do you train on the first epoch and then use that model on the validation set, or every run through, every time you, every batch, you train the model?
In each epoch, okay, in each epoch, we test validation loss and validation accuracy.
Yeah.
And we use that for terminating the algorithm.
Yeah, I'm just
asking. But here we are not terminating. We are running until 25 epochs. So there is no specific termination conditions. All it does is that does optimization on the training set, but computes validation loss and accuracy also.
Oh, I was just checking the procedure on how the validation loss is calculated. So it trains, so it goes one forward pass, trains it, then uses that model that's just been trained on the validation data to calculate the validation loss. Is that correct?
That's correct.
Okay. Thank you.
Yeah. The loss function, we are actually using only training data. That's the only thing defines what are the parameters when you're fitting. But validation will be computed. We will see why this validation will be useful. Right now, we are just observing how validation is done. Okay. That's why we see that it's not really, even though it's increasing, we are not really stopping anywhere, and we will see how we can use it later for regularization and other things. There is a question from Spencer. My training and validation plots are matching almost exactly. Well, I guess that should be okay. If you have, did you change the code or anything, Spencer? That's okay. Okay. Anyone else have the same plot unlike this? And yeah, I don't know. I have run this several times, and this is what I get. And I'm sure if you haven't changed, is there any chance you ran some normalization or something twice without noticing? Yeah, just make sure to run again quickly if you want, quickly from the beginning until this point. And yeah, just clear everything and quickly from the beginning, you can just shift enter. can come to this point. I'll give a minute to do it. Let's do it. Yeah, this just make sure that your table of contents is same as this. If you have downloaded from the website before 9 a.m. today, there is a possibility that you got a older version, and that's a bit screwed up. But up to this point should not be a problem even in that version. So, all right, I hope, okay, a few more seconds, then we continue. Okay, cool. Seems like that's nice. Yeah, it should look like this. I don't think it can be. Yeah, I think somewhere you must have executed a cell twice and that screwed up a little bit. Okay, all good. How it actually predicts on the classes. Prediction we execute obviously on the test data. You can do it in training and validation, but that doesn't really, prediction is about unseen data. Here unseen data is a test data. Let's go with predicted classes. So we are just looking at first, okay, 20 images, and this is the command for predicting model. That is a pointer we have for our model, and predict on this, predict this 20 images. That's what we are asking, and we are storing those classes in predicted classes. I'm sure you guys have seen. Can you guys guess what you might end up seeing here? Do you end up seeing like a nice class classification, like a 0, 1, 5, 3, something, or without executing, someone can tell me? They're not
really small decimals.
Yeah, they're fraction, like they're not really probabilities. And yeah, the probability. Okay, let's look at which one has a maximum value here. Yeah, you're right. It's they give probabilities. So if you look at what position, 0, 1, 2, 3, 4, 5, 6, 7, we expect 7 to be the first class, and like that you have this being these are not actually probabilities. It actually we are using softmax. What happens in softmax if there is a mismatch? Like we need to take maximum, right? Maximum over all possible entries when finally we have. So if you actually do that, predict classes, we are just rounding them and taking argmax, and you see that the position is argmax. Which position has a maximum value in each entry is given for all these 20 images, and as we saw, 7th element is highest, so we have 7, then 2, and so on. And if you compare with actual labels, the true labels, you see that they're matching. Do you see any mismatch anywhere? I don't see. That's good. It's predicting well. Second last. Oh yeah, there is one. That's good. Yeah,
I just have a quick question about the plots. Every time you train, even if it's the same model, will you get slightly different losses? So they'll be pretty much the same, but slightly different, because my plots look pretty much the same to yours.
Yeah, there is a chance. Like If you're running local on your computer and if you're fixing a seed, then
Okay,
you
yeah.
should expect same thing. I'm fixing seed, but still I have noticed that there is a slight change. The reason being, when we execute, I think probably it is putting in different systems.
Yeah.
On Google server. If you're doing it on Jupyter or in R, which mostly you do it locally, you might not see this discrepancy.
Okay, cool. Thank
Yeah. Okay, so this is good. Only one in 20 images, first 20 images, there is a mismatch. And so let's calculate for entire data set. We are not going to print that. That's going to be a big mess. So let's just do the same thing for the entire set. And so we got all the predict classes, and we found labels like after applying Rmax. And this will tell you which class has how many entries. So after prediction, this is a predicted class, we see that the 990 images are classified as 0, 1146 are classified as 1, so on. Okay. And if you look at what actually this class, count for actual labels, if you look at that, you see that in the actual data, test data, 980 images are corresponding to this is 0, whereas our predictor somehow got 10 more from different labels and classified as 0. So there is a confusion here that can be computed using confusion matrix, and it is part of a scale-learn matrix, and that can be computed as follows. We are giving test y and predict y, and it actually creates a matrix, and that can be printed. And we see that 968 true images are predicted as true zeros are predicted as zeros. That's a good number. And zero of them are zero images are predicted as 1. So on, we have most important thing is that these diagonal elements, and these will be defined true positive, and that gives us accuracy. And accuracy just add up all the diagonal elements and what is the magnum number, and you see that accuracy is 0.9768. You might compare with what happened. This is a test accuracy. I guess this is the number we got. Yeah, that's what we got. Okay. Now we have taken 128, 64 is the hidden layer sizes. Now we play with these numbers. We create 9 different architectures, and forget about this. This is just to being fancy and creating, showing that one hidden layer network. For that, we have 3 variants of one hidden layer. One is with 16 neurons, and second one is called medium, and that is 64 neurons, 256 large. So second two hidden layers will have 2 hidden layers, 16, 8, 64, 32 for medium, and 256, 188. Okay, this is the second last is right. So clearly we have different. Yeah, thank you. And just to make it easy, I'm actually defining a function called compiler, which takes a model pointer and compiles exactly how I did compiler earlier, specifying cross entropy and RMS crop, metrics being accuracy, and printing summary. and trainer is essentially fitting a model. And this is exactly doing same thing, because I will be having multiple models, 9 of them. I need to call them rather than defining separately. So let's go one by one. What is a MDL? Just a pointer. MDL is a model essentially. I'm just using a short form. When you call this compiler, whatever model pointer you got, it will be given as input, and it will does compiling on that, and returns nothing, obviously. Okay, and see, this is a small model with one layer, sequential. Just we are doing because we specify that we want small 16, and then output layer has 10 neurons, and the medium size is 64, but only one hidden layer, so 10. The larger one has 256. We have defined these 3 models. For each model, we are compiling again and fitting values. So once you execute this, it actually does create a, I forgot to execute this. So we are running out of time a little bit. I'll take another 10 minutes. Is that okay? If anyone has any other issues, let me know. Okay, thank you. And I think if you have an issue, text a message in the chat. Okay, it's just for each model, it is compiling. This sequential 2 is essentially whatever model we created just here, that it is. And it has these many parameters, and this is a medium size one, and now fitting is happening. How about okay, up to you guys. I don't use Facebook, so that's all right. But Canvas also can be a place for discussion, I guess. You can think of it. Maybe not as convenient as Facebook. I think we're done. So okay, all 3 models are done fitting the data. And now, again, I need to plot these accuracy values for each model. So I'm just defining a function for that. It's essentially putting everything in one function definition. And now print for small model with one layer, that can be printed as follows. And you see that this is how it looks. And for medium, one layer is, this is how it looks. So for small, you see that validation and loss, or validation and training are close to each other. Both are, because we have a less number of neurons. But for the medium model, is already, you can expect, it's not really overfitting, but you can expect if you increase neurons in that hidden layer, you might actually see overfitting, and probably that will what we will see. And we have seen that, and you see there is a suddenly increase in the validation. Okay, I'm not doing this. All you need to do is that you execute this. Okay, we already created these models. You just need to fit similar things. You need to do it for two hidden layers, and then 3 hidden layers. Is that clear? Any other question here? Yeah, you can ask these questions and try to do it yourself once again. Okay, now we are at a batch normalization. I'm sure you guys already read what is batch normalization and how do we do this. So Keras layers, that is a part of Keras, you can import something called batch normalization. and it's easy to do it. What do you do? Let's call this model with norm. Again, we have sequential pointer, and we need to add just earlier, and we are doing normalization immediately after input layer, and immediately after first hidden layer, and immediately after second hidden layer. Okay, there are different ways to do it. Sometimes before input you do it before hidden layer on this thing. You can try different combinations, all are suggested, but normalization generally makes gradient descent work well, as you have read. And again, we have Relu and softmax.
So just to clarify, batch normalization, is that just normalizing to have the data that's going into each layer
Yeah.
to have a mean 0 and variance 1? Yeah, okay, cool.
Okay, that's correct. And now let's compile. And after compiling, we have compiling and fitting value. So see, it's easy to compile because we already defined the function. You see that suddenly non-trainable parameters are 1900. These are essentially the means and variances we calculate at each, which doesn't involve in back propagation. Okay, that's why earlier we have a non-trainable parameters being 0. But if you look at what is actually non-trainable parameters in Keras, you understand that the parameters which are not going to involve in back propagation. Okay, because when you're doing differentiation, you don't consider weights. We don't change this mean and variance. Or if you add all those things, you get this number. Okay, this training is done, and it have you there is a question. So batch normalization used to increase the accuracy or speed up of training. Have you read the lecture notes so far, whatever is discussed in class? No? Yes?
I think it just speeds up the learning.
Yeah, this speeds up the optimization process also.
But it also seems to have less overfitting as the model gets larger, which is opposite to usual. Unless
I think sorry, what is that? Less?
Sorry, no, I just realized the models were opposite. All good.
Yeah, so like in lecture it's mentioned that it does a little bit regularization, but that's not the main purpose. It has given examples of what happens before normalization and after normalization. So gradient descent actually converges faster because of normalization, and as you can see in the example, so that means fitting happens fast. And
so the fitting happens faster, but the outcome should be about the same with the fitting. Is that right?
What?
So does batch normalization do anything to help with overfitting, or is it just to speed up the training?
War fitting is a very generic concept, right? It's speeding up the process, and each. So we are not actually using termination condition here. We are having 25 iterations only in each algorithm. So you see better performance after 25 iterations if you use batch normalization than without batch normalization. Generally, it's not necessary that it's all the case. Okay, and you can compare with this. I think I'll rush a little bit here. And once I'll just quickly describe what we can do, how we do other things. So we are at batch normalization. How do we do regularization, dropout? It's not guaranteed that they can improve immediately, What I will suggest you that take a shallow network with just one layer and see, maybe there we can see performance changing drastically, and I'm guessing. And okay, what is this particular cell doing? Here I am actually defining one layer models, all of them again. Okay. With batch normalization. Earlier, we didn't use batch normalization, but we did in fact define one layer models just like this without batch normalization. So if once we are at home and fit values and see the performance, and if we have doubt, we can discuss later. But it's essentially does the same thing as earlier, but with batch normalization, and you get fitting done. Still doing. So this is it now. Second model. Third model is now going. It's fitting the weights for third model. Should be done. Yeah, from here you can follow code easily. So in any case you need to go, feel free to go, but we'll finish it this part before we leave. All right, it is done, and we can actually see, we can plot the results. Thing is that they already have good results here, 0.978, and that's why you don't see improvement. So I would recommend you to actually go with some shallow, and instead of large, let's take small. How the performance, and let's see how it done. See, accuracy is much smaller than the large one. You see, now look at medium. This is already good improvement, and we have seen large already. That is improving third digit, of course, but better than the medium one. And you see this improvement as we increase the number of sites. This cell actually creates models with two layers, shallow, not shallow, two layers with a small size and then medium size. Go to that table earlier, and you see that this is what we wanted, and then final one has a large model with 256 neurons and 128 neurons. Oh, wait. Oh, I did something. This is not. This is not correct. I added one more. So I'm sorry for that. And this is supposed to be two layers, and remove that line. So two layers, large should have 256 and 128. This is one layer model. One layer model, I think we are good. And two layer, I did some mistake here. Make sure that you remove that 64 thing. That is for next thing. And is there a way I can stop it? No. Okay. Let me do it again. Yeah. Any questions so far? Is this things clear? If anyone is not clear with what is happening so far, please let me know. Not much has changed from the basic deep neural network and with batch normalization. We are just adding batch normalization after each layer. So now it's fitting for the second 2-layer model. Now it's a large 2-layer model and it's already accuracy is 99%. If you're done with executing, execute the other cells also with 3 models, 3 layers. Yeah, now it's done and we can actually see some comparison here. For large, this is the value we have, and let's see what happens with medium. Should be very close to that. So sometimes, yeah, slightly lesser. And what happened with small? Yeah, it's reduced. So there is an increasing order of these things. And this is for third set. And I guess I will leave it to you guys running this. If we need, we'll get back to this. Let's talk about regularization. There are 2 kinds of regularization. I think I'm not actually doing L1 here. I'm sorry for. I'm not sure I'm doing L1. So that's easy. Like it's the same way. How do you define L2? You can define. Anyway. So what we do it now we keep the batch normalization, but we also mentioned that we want regularization and with 0.001. So is anyone not read the earlier lecture notes to understand this? So you have this norm of weights and multiplied with a gamma factor, I guess, in the lecture notes, and that is what it is defined. And now second square of norm, that's why it's L2, and we multiplied with this, and that's how we define L2 norm. This is L2, not 12. It's L2, and yeah, and this is for hidden layers only. We mentioned for we don't apply that on output layer, so we no need to worry about it. And since we are playing with one hidden layer which has normalization, also batch normalization, this is how we define, and you can actually compile again simply and fit values. What I suggest that go, and this is already, so like it already has a very so many neurons, so already good, it has good performance. What you do is that go with some shallow like a few neurons, like 16 or something, and play at home what happens if you use regularization, what happens if you don't use regularization, and the results seems to, if you see this, this increased validation is not too much. So that's what we expect from a regularization. And this is this network is same as model with one layer, okay, small, no, large, without regularization. So we already created that as a model one layer large, and we can actually print and maybe have a comparison. It's not guaranteed that it always improves, as you see here. So that's why I'm saying, like, it already has enough neurons in the one layer. So play with a little bit. But if you notice here, the validation is not increasing so much here. Whereas in the earlier model, after how many, say 5, it is actually increasing. So we don't want this kind of overfitting. See you, Richard. And yeah, that's about regularization. Then dropout. Let's quickly go through this. You have a regularization here, L2 regularization, and when you do dropout, we have seen earlier that dropout, you can actually uncomment this. How do we actually, so I'm assuming that you have read dropout from the textbook. We drop out with probability 0.4. Sorry, we are selecting with probability 0.4. And so, you know, we need to multiply P. Everything is done internally, those weights multiplying with P and then multiplying with 1 over P. And but you have a concept of dropout already, and that can be implemented using Keras. Yeah, the package called dropout. And yeah, okay. And yeah, you just go ahead and run this yourself, and I'm not going to wait for this output now. And again, we can print results. And
I just have a question with the plots for the dropout. Is it normal to have the validation set have the loss and the accuracy better than the training set?
Sorry, say again. Well,
so when I ran the dropout, the validation accuracy and loss is actually better than the training.
Better than the training?
Yeah.
That should be okay. I think that's quite possible. It's not always one is strictly less than that or something.
It just sits above the training one the whole time, unless I've just run something in the wrong order.
Let's see, I'm running the dropout.
Also, the command you have at the end of the code, the keras.backend.clear session, what does that do?
And that is just all the models you created. It's supposed to clear up things. Don't run it now. Yeah. In case.
So just run it when you're finished doing everything, just to clear
yeah,
it
that's
up.
Just to clear it up if you want to have a fresh start or something on the same. Okay, yeah, so we have this. So what is your question? You're saying that
when you plot the results for the dropout.
Okay.
Yeah, the validation accuracy sits above the training accuracy, and same with the validation loss. It's under the training loss.
So that's a better. So validation is better. That's quite possible.
Okay.
That's quite possible.
I just wanted to check that it was possible and the code wasn't just messing up.
No. Okay. I haven't executed this 3 large. So just go 3 large, and because that's what we are doing here without dropout. And yeah, early stop is another sort of regularization thing. Regularization in the sense to handle this overfitting problem, where you don't want to run 25 epochs. Okay, if already you're saying validation loss is actually going up, you don't want to waste, and because you want to take neural network weights where validation loss is minimum. So to do that, it's sort of a termination condition we saw in optimization chapter where you use function on training set, but you actually stop according to the validation loss. And that's what we do. What we do is that early stop, we wait until 5 epochs or iterations when you don't see any improvement for those 5, and you stop there and take the values just 5 iterations before that. That's a sort of minimum. And, okay, and that's you can have this early stopping command from callbacks in Keras, and we are also using initializers. I'm sure, like if you have read the chapter, there is a random initialization. Instead of starting weights and some fixed value, we generate them from a standard normal distribution. That's what he explained yesterday. And we are using standard deviation being 0.01, and L2 regularization we are using again. And what we are doing here is that early stopping that will be will be defined in fitting. Okay, this is important while fitting. So fitting also takes these callbacks. If you mention that early stopping, patient being 5, it will actually if like validation loss is increasing consecutively for 5 iterations, it will actually stop and then take the minimum value. That is what we see here. If we asked it to run for 25 iterations, but you see that it actually terminates even before that. Hopefully, that's what it did yesterday. Come on. Yes. Yes, it did. See, 16. And again, print and yeah. Cool. I think, yeah, that's about it. You see, this is after this 5 consecutive times, it actually increased. So it actually stopped after this. But some other places it increased, but it's not 5 times increase. It just a couple of times, and again it decreased. So it was happy. And yeah, that's about today's practical. Go play with it. I hope this course will be helpful for you to work with, start working, and you play with other possible options in Keras, and hopefully you learn something today. Any questions? I know it has been taking a lot of time.
Thanks,
Thank you. Thank you. Andrew?
Thank you. See you later.
You have any question, Andrew?
No.
Thank you. Yes, good time. Let's get ready for quiz. See you guys.
Bye.
Bye. Have a good day.